Greetings Redlings and welcome back. In this video I'm going to talk to you about reliability engineering and process safety. This one came about as a result of a training course that I've been doing recently, and I'm really keen to share this with you because it can shed some light on a very important topic. Of course, before we get started, if you're new to the site, you know that we have an app which you can download, Safer Working app, which is www.saferworking.com. And of course, sometimes, not always, we have a quiz that's related to the content that's on this video. So please feel free to visit the website, have a go, and check out your scores relative to pre-video and post-video. Let's dive in. Let's start first with joining some dots. Firstly, what exactly is process safety? And then we're going to look at what is reliability engineering and some important facets associated with that. We're then going to take a trip down introducing RAM. What is it? Let's look at some equations and also applications. And how can reliability engineering support process safety improvement? And I'm going to wrap it up with some conclusions. Let's start first with what is process safety. As you know, I've done tons of videos on this, but in essence, process safety just refers to the prevention of unintentional release of chemicals, energy, or other potentially dangerous materials during the course of chemical processes and reactions, which can of course have a serious impact on safety and also the environment. This is a usually typical chart that you see of process safety versus occupational safety. I think the most important thing to recognize in this is that process safety has high consequences, but there are low probabilities of it happening. We don't want a Chernobyl or a Texas refinery or a Bhopal every day of the week. On the other hand, occupational safety has lower consequences, not that I'm demeaning any incidents or accidents to people, but it has, of course, a greater likelihood of happening. So the fundamental difference between process safety and occupational safety falls down to consequences versus likelihood in terms of high or low consequences and high or low likelihoods. Now let's look at process safety impacts. Process safety has far wider reaching impacts than occupational safety. In occupational safety, you're looking at individual issues or impacts such as slip, trips and falls and accidents therein. But process safety has far wider reaching in terms of asset damage, reputational, financial, environmental, loss of life and also production. As you can see, if you have the process safety incident, then it is of course far catastrophic in terms of impact and also wider reach. Now when it comes to reliability engineering, and I don't want to dumb this down anywhere, and my apologies to reliability engineers out there if I have, my intention is really to put it into a sort of a wrapper just for process safety. There are three key sort of focus areas that we can consider. One, of course, is the reduction or elimination of production losses. There are some texts in here that you can stop and read at your leisure. The other one is to identify and manage risks in the areas of strategic business objectives. That includes HSE, cost, production, and reputation. There are lots of analysis tools that can be used for doing that particular analysis. And in terms of another focus area, it's all about asset life cycle management, because every process plant or production facility has a lifetime of operation. So we want to manage the assets that are in that particular bubble. Now, our three focus areas are really on three definitions that come out of reliability engineering, and they are specifically to do with reliability, availability, and maintainability. But what exactly are these? And I want to dive into each one of these separately and sort of create a little bit of storyline behind it to give you an idea of what exactly they are. So let's start first with reliability. As it says, it's the probability that an asset will perform its intended function for a specified time interval under stated conditions. The metric that is commonly used for this is the mean time between failure. And that's a very simple equation. It's the operating time divided by the number of failures. So if a plant has 2,000 hours of operating time and there have been 10 failures, that's 200 hours per failure in terms of mean time between failures. Now we need to look at availability, and that's a degree or percentage of time probability that an asset is in the operating condition. And of course we have a metric. Availability is the time in operation divided by the time in operation plus the downtime associated with it. If you consider a plant over a year, 8,000 hours that it's been operational, and there's been, say, 760 hours of downtime, then its total availability is 91.3%, as shown by this equation here. A very important equation is this in terms of availability, because it's what the bean counters are really quite interested in. But of course, plants do break down, and we need to have a maintainability metric with it. And that's the asset's ability to be restored or repaired to a specified condition by people with the skills and, of course, using resources and procedures that are in place. A metric for this is the mean time to repair, and that is the average time to repair the asset. Very simply, if you have 2 repairs on a plant and it's each taking 10 hours and 20 hours, then the total time that it's been down is 30 hours. So therefore, the mean time to repair is just the 30 hours divided by the number of repairs it's had, which is 2, and therefore the mean time to repair is 15 hours on this particular sort of scenario. Rapidly went through those equations, but let's put it into some context here. So for example, in a calendar year, which is 365 days, car, say, let's had 2 times 2 failures. So the first time the car was in the workshop 4 days, and the second time was in the workshop for 6 days. So the RAM details are as follows. Reliability, very simply, is just the mean time between failure, and that's the operating time divided by the number of failures. So out of 365 days, it was down 10 days, and there was 2 failures. So the MTBF is 177.5 days. Availability is therefore just the time in operation by the time in operation downtime. Simply put, 365 minus the 10 days it was down over the 365, giving you 97.26%. And finally, maintainability is just the mean time to repair, average time to repair an asset. So it's had 2 repairs, and that's 10 days, so that's 5 days per repair. Do stop this video and please take these equations into account. They're fairly straightforward, but they're very powerful in terms of giving you an insight into the workings of a facility, a manufacturing plant, chemical plant, whatever you want to think of. Let's add a bit of clarity here, because there are 2 things I need to distinguish, and that's defects versus failures. A defect is something that may lead to failure in the future, whereas a failure is something that isn't working now. Very important concepts, because correcting a defect early is of course substantially less in terms of impact than doing something as a failure. If, for example, it costs you $25 or pounds, whatever you want to think of, to correct a defect, if that's left unattended, you could be looking at substantially more, maybe $25,000, etc. I'm giving you an example here, but I'm thinking specifically there maybe of a compressor. But there are other pieces of equipment that have similar sort of a relationship. And the fundamental point here is the cost in terms of losses, etc., as a result of failure versus early warning correction through defects. There is a curve that we can also consider when we think about reliability engineering, and that is the deterioration curve, or some people call it the PF curve. Here is the PF curve. A little bit complicated, but let me try and explain as best as I can. We have 2 axes, the condition here and the time. When you buy something brand spanking new, of course, you start to do your inspections. But like everything has a sort of planned obsolescence or a failure point. And as you do more and more observations, it will come to a point known as P. This is the point where we can find out it is failing, the potential failure point. In many cases, there's a rapid decline after that where we head towards a failure, and that is the PF interval. And the point where it has failed is called functional failure. And if it's not taken care of and it says bang, as you can see on this diagram, it can, of course, result in a bang. The main point of this deterioration curve is to emphasize that everything does have this sort of a relationship. And if you do detection and taking care of things at an early stage, you can, of course, extend this time point before it starts to potentially fail. So this curve, the deterioration curve, is very useful when it comes to looking at equipment and also details on how it performs. From a RAM perspective, we need to look at analysis, and analysis is reliability is key to preventing undesired events instead of letting systems failures happen and dealing with consequences. So a structured approach gives you an opportunity to be one step ahead of the rest. You want to try and catch it early. You want to try and catch it in terms of detection rather than the failure. So a solid design based on maintainability concept will make sure that the harmonization of maintenance tasks leads to minimum cost and downtime, adding lifecycle value to every stream. And of course, safety analysis and risk assessments minimize exposure of safety systems and users to undesired events. There are lots of tools that we can use in reliability engineering and also in process safety. I'm just doing a quick touch and go here just to give you a feel for these things. FMEA is failure mode and effect analysis, which we can use in reliability engineering. There are also things like FMECA, FMEDA. As if I haven't drowned you with enough acronyms, I'll throw a few more in there. And there's of course fault tree analysis and reliability block diagrams. These are all tools in the armory of reliability engineers, and they work closely also with process safety specialists. But of course, process safety specialists have their own sort of set of acronyms not to be beaten. And we have HAZOPs, we have layers of protection analysis, and also process hazard analysis. I'm not going to go into too much in detail in these tools and techniques because over the course of the coming weeks, certainly on this channel, I'm going to explore these in more detail so that you can ping backwards and forwards and pick the videos of your choice. So in conclusion, we know that I've only given you a snapshot into the world of reliability engineering, and RAM can be summarized as dependability. If you do reliability, availability, and maintainability, you're looking at improving the dependability of those assets. It's quite deep and detailed analysis with specific tools can be used. I've given you a snapshot earlier, and many companies now consider the S at the end to make it RAMS. In other words, reliability, availability, maintainability, and safety. Don't get confused with RAMS with other acronyms out there, which I know you're very familiar with, especially in the construction industry. Canva apologize, acronyms ahoy, but hopefully this is a small snapshot of how reliability engineering and process safety can support each other in terms of reducing process safety events, loss of primary containments, and also process safety incidents. Once again, thank you for stopping by and listening to the video, watching the video I should say, and also do drop me a line if you've got any thoughts, subscribe to the channel, and if all else fails, download the free app Safe for Working at www.saferworking.com, and let's connect, share, and learn. Thanks, till next time. Bye for now.